Okay, good evening. I'm Mr. Glante once again. Today's lesson is going to be on physical and chemical change, which is a subsection under matter and materials. As you have observed, most of the things are matter and materials, matter and materials. So this one is called physical and chemical change. Now, even though our emphasis is going to be on chemical change, we will still have to talk about physical change. Now, to understand physical and chemical change, we first have to look at what change is. Now, change is something that you are familiar with. If you don't know change, just look at your picture when you were a baby and then your picture as an adult or maybe a teenager now. You will see that you look bigger, you look taller, you look stronger. So something has changed. As far as chemistry is concerned, we distinguish between two types of changes. We have what we call physical change and chemical change. So we start with physical change. What is physical change? Physical change is a change in which no new substances are formed. Physical changes usually involve a rearranging of molecules. So the molecules are moved around, but the molecules are not broken apart. In other words, they are intact. You just shuffle them, you reshuffle them like you are playing cards. You move them around, but you do not break the molecules. Okay. So we refer to that as physical change. Now, let's look at some examples of physical changes that we can easily relate to. The first one, which is arguably the most popular one is what we call change of state, which we did extensively previously. If you recall, we did the states of matter, we spoke about solids, liquids, and gases, and then we did a lot under that. So this is change of state. So if you have a solid, let's say ice in the fridge, and then you bring it out and leave it out for a while, it melts. So the solid ice or the ice has melted into liquid water. The water still remains the same. The chemical formula is still the same. It's still water. However, the shape has changed. And so such a change is referred to as a physical change. So most of the physical changes, I think you should take note of this particular example, change of state, especially in past questions. They like bringing examples that involve changes of state, solid to liquid, liquid to gas, or vice versa. So when you see that, you just know that this is a physical change. Then another one is dissolving or dissolution. When you put something in water, like sugar in water, it dissolves. It is a physical change because when you heat the water evaporates, and then your sugar or your salt would remain in the container or whatever you use to heat it. So dissolving is a physical change. Then we have conduction. Conduction, materials such as metals conduct heat and electricity. So let's take heat, for example. That's something that you can easily relate to. If you have an iron, the iron that you use to iron your clothing, if you plug it and you heat it, it becomes hot. After a while, if you unplug it, it becomes cool. So nothing has really changed. It's just heating. So it's also an example of a physical change. Then we have what we call separation of mixtures. We did that extensively. We spoke about evaporation, distillation, and so on and so forth. They are all physical changes. Okay. And the last one I want to talk about is physical deformation. If you cut something, if you bend it, if you stretch it, all those things are collectively referred to as physical changes because you can always reverse them in most instances. Now we are going to look at the main substance of what we are going to talk, and that is a chemical change. What is a chemical change? To begin with, I would say that all chemical reactions are examples of chemical change, and we'll see a number of chemical reactions very soon. So a chemical change is defined as a change in which new substances are produced. It involves breaking of bonds. We spoke about bonds previously. I'm talking about ionic bonds, covalent bonds, and so on and so forth. So in a chemical reaction, old bonds are broken and new ones are formed. As a result of that, you have new substances being produced. So we refer to that as chemical change. Now we are going to look at a number of evidence of what we call a chemical reaction. How do we know chemical reactions have taken place as compared to a physical change? One is the evolution of gas. Anytime you make something and a gas is being produced, it is likely that that reaction is a chemical reaction. Another example is the production of odor, smell, whether it is a nice smell or a bad smell. It tells you that a chemical reaction or a chemical change is taking place. And then you have what we call change in color. If something is white and it becomes blue, it tells you that a chemical reaction has taken place. Then we also have something like sound. Sometimes some reactions produce sound. You might hear a pop sound or an explosion. Again, that tells you that a chemical reaction is taking place. Then we have change in temperature. But this change in temperature, you have to be careful because even physical changes involve change in temperature, but usually chemical changes involve significant changes in temperature. So that is important. Then some chemical reactions result in the production of light. You might see light, a spark of light being produced. And the last one I want to talk about is the formation of what we call precipitates. Precipitates are just substances that settle down. So if you take muddy water and then you keep it for a while, it settles down. We say it forms some kind of a precipitate. So the thing leaves the solution and then settles down at the bottom of the container. We call that precipitation. So that is an example, or that is another, an evidence, one of the many evidences, if there's a word like evidences, about what, when a chemical reaction or chemical change has taken place. Now we are going to look at the types of chemical change. Chemical change or chemical reactions. I prefer to say chemical reactions. Types of chemical reactions. Okay. There are a number of them, but the first two are the most popular and the ones that they usually ask in exams. So if you cannot remember all of them, at least the first two you should be able to remember. So the first one is called synthesis or combination reactions. Now, to synthesize means to produce, to make something like photosynthesis, okay? So a synthesis reaction occurs when two or more substances combine to give you a single, more complex substance. So you have a general formula here. You have A plus B to give you AB, 1. So you have two or more coming together to give you a single, more complex substance. Such a reaction is called a synthesis reaction or a combination reaction. In fact, they often say synthesis. So just get used to this word synthesis. So I'm giving you a number of examples here. Here you have ammonia reacting with hydrogen chloride, and then you are forming ammonium chloride. Okay? This is an example of a synthesis reaction. Why? Because ammonia is one substance, hydrogen chloride is the other, and when they combine, they give you one substance. One, not two or more, just one. We call that synthesis. And then you have this example here, you have this combining with this, and then you have one product. It's called synthesis. Okay? Okay, then we have what we call decomposition. Now, decomposition is the opposite of synthesis. So whereas synthesis involves combining something or a number of substances to produce a product, when you talk about decomposition, you are breaking it down. Compose is to bring together. Compose is like synthesis. And then the D means the opposite of composition. So you have, for example, in the case of this, you have AB breaking down to give you A plus B. Okay, usually it is initiated by heat. So we use the symbol delta to show that heat is applied. Okay, but you can also use light, electricity, and decomposition can, okay. So you usually have one substance, break it down to give you two or more substances. So that is the composition. One substance breaking down to give you one, two, three substances. So we call that decomposition. Now, a less popular one in terms of the kind of questions they ask in exam is what we call displacement. Now, as far as displacement is concerned, we have single displacement, also called replacement, and double displacement. Now, in this one, you have one element replacing another in a compound. So we have a general formula like this. You have a compound AB combining with this element. This one takes the place of B. So you have AC now, and then the B is removed out. Okay? So that is called a single displacement. And you have examples like that. This one, you see, this one now combines with the sulfate to produce copper, zinc sulfate, and the copper is displaced, it is removed, and then you have copper. The same thing happens here, and then the iodine is removed and is replaced by the chlorine here, and then you have that. Then we have what we call double or double displacement. With this one, ions are exchanged. In other words, you see you have A, B, C, and D. This takes the place of B, B takes the place of D. So you have A combining with D, and then B combining with C. So that is that, and you have examples here. And then the last one is combustion. Combustion simply means something burning in oxygen or something combining with oxygen. So if you see any reaction where it's something plus oxygen, we call that combustion. Combustion. Anything plus oxygen is combustion, and it's called an exothermic reaction. Exothermic reaction. It's a reaction in which heat is generated. It means that the substance or if you are performing the experiment in a beaker, the beaker becomes hot. So we call that an exothermic reaction. However, like I said from the beginning, please focus your energy, your understanding on the first two, because virtually all the past papers I have seen, and I will be giving you examples as I usually do, is these two which are important: synthesis, decomposition. So if you cannot remember the others, at least these two you should remember. Okay, so now we're going to compare physical change and chemical change. Like I gave you in the definition, in physical change, no new substances are formed. So we say no new substances are formed or produced. For chemical changes, new substances are formed or produced. Now, the energy involved in physical changes are usually very small. The energy change are usually very small. However, with chemical changes, the energy changes are usually high. And physical changes are relatively easier to reverse. So, for example, like I said, if you have ice in a fridge, you bring it out, it melts into liquid water. If you take it back to the fridge after a while, it becomes solid again. So it is reversible. They are generally reversible. Chemical reactions or chemical changes are reversible, but they are difficult. They are not as simple as physical changes. Then there is something else that I want to mention. This one, you don't really have to worry yourself so much because you might get confused, but I'll just mention it. As far as physical change is concerned, the mass, the number of atoms, and the number of molecules are conserved. It means during a physical change, whatever you started with, you are going to end with it in terms of mass, the number of atoms and molecules. A similar thing happens with chemical change. The mass and the number of atoms are conserved. However, the number of molecules are not conserved because there is a change. The molecules you started with will not exist as products. So basically that is it. Now let me move to what we refer to as the laws of chemical combination. There are a number of laws, but at your level, we recognize only two types. The first one is called the law of constant composition. The law of constant composition. Let me tell you something. Definitions from your textbook or what your teacher would tell you would be maybe different from what I'm going to give you now. So don't say that, well, our teacher defined it in one way or the other. It's irrelevant. It doesn't really matter. the idea or the concept behind this is what is important. So the law of constant composition basically says that all pure substances contain the same elements in the same ratio or proportion. In other words, if you take water in South Africa, pure water in South Africa, it will be the same as pure water in China. It will be the same thing as pure water in America. The formula of water would always remain H2O, regardless of the source, regardless of the sample size, regardless of the type of method of preparation. It will remain the same. So it's just common sense, okay? So that is the law of constant composition. Now, the second law is the law of conservation of matter or the law of conservation of mass. This one says that matter cannot be created or destroyed, but may be changed from one form to another. Now, of the two, this is what you have to cram. Try and memorize this because virtually all questions that involve physical and chemical change, they would usually insert this part and say, state the law of conservation of mass or the law of conservation of matter. So find a way to to memorize or cram this one. Now we're going to talk about balancing of chemical equations. Balancing of chemical equations. A chemical equation is used to represent a chemical reaction. And as I alluded to earlier on, a chemical reaction is basically an example of a chemical change, or a chemical reaction involves chemical changes, obviously. Now, we are going to look at how to represent chemical changes. Now, a typical chemical change is written as something like this: A plus B to give you C plus D. Your A plus B are called reactants. Reactants. And then your C and D are called products. Okay? The reactants and products are separated by an arrow. This arrow means it's almost like equal to in mathematics, but we don't say equal to here. So A plus B equal to C plus D. So we use this arrow. Sometimes, so this is how it is represented. But then you can also represent a chemical reaction in word format. So for example, let me say hydrogen, let's say hydrogen plus oxygen gives you water, okay? Someone can also write it like this: hydrogen plus oxygen gives you water. So even if you see it in word format, you have to change it into this symbolic form and then use it to represent. So basically what I'm saying is that if it is written in word format, don't be scared and say, what is this? Just write what hydrogen is, what oxygen is, and then you write it like that. Okay. So sometimes to make your equation more scientific, usually we indicate the state. So if you see G, maybe A, and then they put G under here, maybe L here, maybe AQ here, and then maybe S here. Your G means that it is in the gaseous state, it's a gas. Your L means it is a pure liquid, S means it's a solid, and AQ means the substance is dissolved in water. If you put something in water, you have to indicate it by AQ, okay? So these are the subscripts that you may find. Now, what is balancing of chemical equations? Let me clean this. I think it will be a bit sleeping. I thought I deleted it. Now, we balance chemical equations to make sure that it conforms with what we refer to as, or it obeys what we refer to as the law of conservation of matter or the law of conservation of mass. You see, in science, there is no magic. Whatever you start with, you must end with it. For example, let's say you are 20 students going on a tour from one province to the other. When you arrive there, you find out that instead of 20 students, you are 18 students. You'll be shocked. Your teachers would have to look around and find out who is missing. So the same principle applies with respect to science. when you start with reactants, the products must contain those reactants in the right amount or quantity. Okay, so that's what I'm talking about. Now, there are many rules for balancing chemical equations. There are a whole list of them, but the most important thing are just two most important rules. The first one is that every atom on the left-hand side, LHS means left-hand side, must appear on the right-hand side. So the left-hand side of the equation is before the arrow. Anything before the arrow must also appear on the right-hand side. That is anything after the arrow. In other words, the reactants and the products must contain the same type of element. You don't insert something that did not exist initially. Then the second thing is that the number of atoms on the left-hand side must be equal to the number of atoms on the right-hand side, okay? Now, there are certain chemical reactions that are naturally balanced. In other words, there is no need to balance them. For example, if you look at the first one here, carbon plus oxygen gives you carbon dioxide. If you look at the number of carbon atoms here, it's 1. The number of carbon atoms here is also 1. So it is balanced. Oxygen is 2, here 2. So it's balanced, okay? We can go through the whole list, but it's not really necessary. These are just examples of chemical reactions that are already balanced. What I am interested in is the ones that are not balanced, and we are going to look at how to balance them. Now, when you are balancing an equation, you are only allowed to put numbers in front. We call them coefficient. So you can put numbers in front here, numbers in front here, numbers in front here to balance. You don't change the formula. You don't write something here, put a subscript there in order to balance it, okay? So we will see examples and then proceed with that. So let's look at the first one. Here we have hydrogen plus iodine to give you hydrogen iodide. If you look at the number of atoms, not molecules, the number of molecules are what you write here. Whatever is in front here, if it is 2, it's 2 molecules. If this is 3, 3 molecules. If this is 4, 4 molecules. But we don't use the molecules. Remember I said the molecules are not conserved. So don't use the molecules and say that, we use atoms. So if you look here, there are 2 atoms of hydrogen and 2 atoms of iodine. On this side, there's only 1 atom of hydrogen and 1 atom of iodine. So it is not balanced. Whatever you start with, you must end with it. So we have to increase that. Now, someone will say, why don't we write something like this? Hydrogen 2 and this, something like this, okay? This doesn't exist. This formula doesn't exist. It doesn't mean anything. It's total nonsense. So we don't write that. We put numbers in front here. So we put 2 here. When you put the 2 here, the 2 affects the whole thing. It's like writing 2 into brackets, maybe x plus y. The 2 affects the x and also affects the y, like we do in mathematics. So this is 2x plus 2y. So placing 2 here affects the hydrogen as well as the iodine, okay? So how do we read? We say that there are 2 hydrogens here, and there are 2 times 1 hydrogens here, so the hydrogen is balanced. Then we look at iodine. There are 2 atoms of iodine here, and there are 2 times 1, also 2, so they are basically balanced. So this equation is balanced. Now let's move to that of water. With respect to water, you can see that there is, again, let me shift this one here so that I can write whatever I want to write it from. Okay, so if you look here, you will see that the number of atoms of hydrogen here are 2. The number of atoms of hydrogen here are 2. However, the number of oxygen atoms here are 2, but there are 1 here. So we have to increase it. So we write 2 here. We do not write it like this. Someone will say, why don't you put it like this? I said, you do not put numbers down here. The subscripts are not allowed. In fact, when you do that, this one is no longer water. It is called hydrogen peroxide. So you're introducing something that is not even supposed to have been produced by the reaction. Okay? So don't write, always write numbers in front here. Now, when you put this 2 here, the 2 affects the whole thing. So your hydrogen becomes 2 times 2. So you're going to have 4 hydrogens, and then the 2 times 1. Usually when you write something like this, oxygen, it's like putting oxygen 1. We don't write it. Just like you don't write 1x plus 2y. Just say x plus 2y. So when you see something like this, you should know that there's a 1 there, but we don't write it, okay? So let me put it that way. Okay. So this 2 affects both the hydrogen, it's like putting it in a bracket, as I indicated earlier, as well as the oxygen. So the hydrogen becomes 2 times 2, which is 4, and the oxygen is 2 times 1, which is 2. So the oxygen is balanced, okay? The oxygen is balanced, is 2. However, the hydrogen is now 4. So we have to come and also increase this one to 2. Now, when you do that, hydrogen is 2 times 2 is 4. So it's 4 here. And then on this side, it's 4 here. On this side, it's also 2 times 2, 4. So it's balanced. Oxygen is 2 here. Oxygen is 2 times 1 is also 2 here. So this one and this one are balanced. This one and this one are balanced. So the whole equation is balanced. Okay? So let's look at a few other ones here. When you look at this one, you will see that nitrogen here, let me increase, let me be like this. Okay. Okay. So when you look here, you see that nitrogen is 2 here. There are 2 atoms of nitrogen, only 1 atom of nitrogen. So we would quickly put 2 here. So the nitrogen is temporarily balanced, or is balanced for now. However, by placing 2 here, it affects even the hydrogen. So the hydrogen is now 2 times 3, which is 6. But on this side, we are 2. So you have to come and write 3 here. Okay? So come and put 3 here. So that is now 3 times 2 is 6. 2 times 3 is also 6. The nitrogen here is 2. The nitrogen here is 2. So this one and this one balanced, and then this one and this one are also balanced. So this equation is also balanced. Okay. Then we go to the next example. The next example, you have that. Let me separate it again, that we see what we are doing. Again, when you look at this one, you have sodium, oxygen to give you sodium oxide. Let me separate this one. Okay. So the number of sodium atoms on this side is 1. 1. We don't write it. It's 1. Okay. So, but on this side, it is 2. So in order to balance it, we write 2 here. Oxygen is 2 here, but oxygen is 1 here. So we need to do something here. So we put 2 here. So by putting 2 here, the oxygen is now 2, but the sodium is now 2 times 2, which is 4. But here it is 2. So we have to come and cancel this one here. And then we put 4 here. Okay? So we put 4 here. And therefore, this becomes 2 times 2. The sodium is 4 here. It's 4 here. Oxygen is 2 here. And this is 2 times 1 is 2 here. So it is balanced. Okay? Then we look at example number 5. Iron plus oxygen gives you that one. Again, let me shift them so that there will be some spaces to write. Okay. So what do we do? If you look here, you see that iron is 2 and iron is 1 here, iron is 2 here, so we can put 2 here. Oxygen is 2, is 3. So we have to do something, but we can put 2 here. By putting 2 here, the oxygen is now 2 times 3, which is 6. So we can put 3 here. 3 times 2 is 6. However, like the previous one, the iron has now increased. 2 times 2, 4. So we come back here, And then we erase this one and put 4 here. Okay, so that's what we do. There are a few other examples here that I'll just go through quickly. Then we proceed. Again, you have something like this. Here, there are 2. There are 2. I mean, phosphorus here is 4. Phosphorus here is 2. So we can put 2 here. So 2 times 2 is 4. So 4 is balanced. However, the oxygen is now 2 times 5 is 10. Here is 5. So we put 2 here. So 2 times 5 is 10. 2 times 5 is 10. So we have basically that. Okay. And that is that. Then we come to the next one here. We come to the next one here. Okay. Let's look at this. Just okay, so let's look at this one. Let's see something. Excuse me, let me just check something quickly. This one's 2, yeah, 3. Okay. So let's look at this one. Now, if you look at this carefully, we would say that, let me take this one out. It's going to be too long. Now, if we look at this one, we would see that aluminium combines with chlorine to give you aluminum chloride. Okay? This one is 3, this one is 2. So we can put 2 here. By placing 2 here, the aluminium becomes 2, the chlorine becomes 6. So you come here and put 2 here. And then, so this is 2, this is 2. However, the chlorine becomes 2 times 3, 6. So we need to put 3 here. And the last one we are going to do is this one. You look at sodium here. Sodium here is 2, here is 1. So we place 2 here. And then by placing the 2 here, remember the sulfate is the same sulfate here. So the sulfate is not changing. So the only thing that is changing is your oxygen and hydrogen, and then the hydrogen here. Now, if you look here, you're going to have 2 or oxygen, another 2 hydrogen, and then you have 2 hydrogen. Okay, so the hydrogens are 4 and the oxygens are 2. So we can put 2 here. Then it's 2 times 2 gives you 4. And then the oxygen has also increased to 2. So the equation is balanced. Yeah. Let me say that balancing of equations involves what we call try and error. You have to practice a lot to be familiar with what you are doing. But let me show you a certain trick, another trick that can help you. And let me use water as an example. You see, in the case of water, we had hydrogen like this plus oxygen to give you water. Okay. Now, because the hydrogen is balanced here, you see, hydrogen is 2 here. The problem is with water. O, okay? Here it is 1 and here it is 2. So we can use fractions, okay? We can use fractions. We can write a fraction like this, half. Half of 2 is 1. So it's like this one will cancel this, and that will be 1, which is equivalent to this. But then you don't leave it like that. You multiply 2 by 2 to get rid of this, okay? So this one is going to be, so it's going to be like this, hydrogen here times 2 plus your original half times 2, and then you have your oxygen here. So this one and this one cancel out. So you are basically left with 1. And then this side, you also multiply by 2. So you have that. So sometimes fractions can help. The fractions involved, usually the most common ones are quarter, half, 3/2. You can use them for purposes of balancing chemical equations. So these are the main examples that we are going to talk about. So we're going to finish up by looking at real examples, real past papers like we usually do to see what is going on. Okay. Okay, so the first question says that the unbalanced equation I and the word equation II for two chemical reactions are shown below. So you have the two chemical reactions there. And then you are asked to 6.1 says, which one of the above I or II represents a decomposition? I told you decomposition is something breaking down to give you others. So the first one cannot be decomposition. It has to be the second one here. Okay, decomposition means one substance breaking down to give you two or more substances. So this one is your decomposition. I. And obviously the first one is synthesis. I told you, make sure you know at least the two. So this one is I. Okay. This is I, and this is I. Okay. Then the next thing says that what does G represent in I? You look here, there is a G here. G, G, G. You say it means that it is a gas. Gas. I told you G means gas. If you have forgotten, let me just quickly go back so that you see what I'm talking about. Here, I showed you, yeah. Here, see, I said when you have a subscript G, it means gas, L a liquid, S solid, AQ means it is dissolved in water, aqueous. Okay, so your G means that it is in the gaseous state. It's a gas or in the gaseous state. So if you don't want to use the word gas and you want to be sophisticated, you can say that it is in the what? The gaseous state. Okay, gaseous state. I'll just say gas to make things very simple. Then this one says that write down the balanced equation for write down the balanced equation for the word one and show all the faces. Now, this one is a bit unfair, but they just want to know whether you are familiar with your sign. So the first one is, we are talking about this. See, this one. So it is written in word format and you are supposed to write it. So calcium carbonate, the formula for calcium carbonate is, so this is 6.3. The formula for calcium carbonate is like this, calcium carbonate. We learned about how to write the formulas of compounds earlier on. So that one gives you calcium oxide. It's written like this. Calcium oxide plus what? Carbon dioxide plus carbon dioxide. Okay. Now these ones are solids. It's unfortunate you may not be familiar with it, but at least you know that carbon dioxide is a gas. So this is solid, solid, and gas. So this is what they expect you to write. Then the second one says that rewrite one in your answer book and balance the equation. So SO2 plus, so let me go to this. This is S4, 6.4. It says it's SO2 plus oxygen to give you SO3. Now, this is one of the examples where you can use fractions to make things much easier for you. Okay? if you look at this carefully, you will see that your sulfur here is only one atom of sulfur here, another one atom of sulfur here. But the oxygens are 2 plus 2, 4. Here it is 3. So in order to reduce it to 3, we can put half here. Half here. Half of 2 is 1. So 1 plus 2 is 3. Okay. However, you don't leave it like this. You multiply 2 by 2 to make it balance. So we put 2 here. If you multiply this by 2, it cancels out. And then this one becomes 2. So the balance equation becomes 2 SO2 plus oxygen, because that 2 cancels the half, they cancel out. And then you have 2 SO3. So this is what they expect you to write. And then the equation is balanced. Then the next one says that name the chemical law that a balanced equation illustrates. So we say it's called the law of conservation of matter. We say law of conservation of matter or mass. Okay, I stated it earlier on. It says that matter cannot be created or destroyed. I gave you 2 laws. Second one I said was very important. Let me just show you so that you know that I have just taught you this. Okay? Yeah, these 2 laws. Laws of chemical combination. The first law is law of constant composition, which I explained. And I said, focus on this one, law of conservation of matter. This is what is used to balance chemical equations. So we rush quickly to this one. And then we write law of conservation of matter or mass. You don't have to write matter, you write what law of conservation of mass. Then done. Then it says using equation 1 above, show that the mass is conserved during the reaction. So this is 6.6. Yeah, 6.6. Now this one takes, let me start from here because it's going to be, so we are going to use this equation that we have balanced here. This one, this equation. Okay, maybe I should write it again so that you see what is going on. So this is 2 SO2 plus O2 to give you 2 SO3, okay? So to prove it, this is how you do it. I think I'm only answering one example, and then subsequent ones, I'll just leave it for you to, or maybe I'll just show you a highlight. You start by saying, I told you that whatever comes before this one, we call that reactants. So these ones are called reactants, and whatever comes after the arrow, we call that products. So you say that mass of reactants, calculate the molar mass, the masses of that. So you write 2 here, and then you put this one, okay? Your S, the atomic mass or the relative atomic mass of sulfur is 32, okay? So you put 32 here. 32, this you get it from the periodic table, it's not from my head. Then plus oxygen is 16. So there are 16, but there are 2 of them. 16. Remember, one oxygen is 16, the other oxygen is 16. So 16 plus 16 is 32. Okay. Then we come to oxygen here. Again, oxygen is 16 atomic mass. The relative atomic mass of oxygen is 16, but there are 2 of them. So we multiply by 2. So when you do this, eventually, when you do all this, I'm giving you the answer because I've done the calculation already. I don't want to waste time. This is just mathematics. You are going to have 160 grams, okay? And then you come and say mass of product. Mass of product. The product is this one. excuse me, the product is this one, SO3. Okay. So mass of product is equal to 2 into brackets 32. Okay, let's see if we make it like this so that it doesn't confuse us. 32 for the sulfur. Remember, this is what I'm talking about. This 2 here is what I have written here. The 32 is for the relative atomic mass of sulfur is 32 plus oxygen. Oxygen is 16, but there are 3 of them. So it's 16 times 3, okay? So when you do this, you will also get 160 grams. So you end up by saying that this one is the last one. It's always 1 mark. You shouldn't end here and assume they know, right? Therefore, mass of reactants is equal to mass of products. This one always carries 1 mark. Okay, so don't forget it. Even if you can't perhaps do the calculations well, just make sure that at the end you say, therefore, mass of reactant equals to mass of product, and then there will be a mark allocated to you for that. Okay, so let's go to the next question. The next question says that study the following diagrams and answer the questions, the question set. So you have this symbol here for oxygen, this symbol here for nitrogen, and this symbol here for hydrogen. So when you see these diagrams like this, it's always good to come and write what you see here. So these ones would be 3, all these ones here would be 3 hydrogens, okay? And this one here is nitrogen, even though it doesn't look the same, but of the other ones, you can see that this is the closest. Okay, you may not see it well, but this is the closest. So this is 2 nitrogens. And then when you look here, this is ammonia, because it's nitrogen plus 3 hydrogens. So we say this is 2 ammonia, NH3. Okay? Then when you look here, these are just, this is oxygen. So this is oxygen and these are hydrogen. So this is water. And this is also water. Now the question is, identify the letter that represents a physical change. The answer is B. The reason being that here is water, here is water. The formula of water hasn't changed. The chemistry of water has not changed. However, whereas in this situation, the molecules of water are compact, they are packed together, they are close together. So this is likely to be ice because they are packed together. In this case, they are separated. So that is a physical change, maybe from solid to liquid or from solid to gas. But at least you can see the difference that here they are packed together, here they are separate. So this is a phase change. And a phase change is an example of a physical change. So this is when I talk about phase change, I'm talking about change of state. So B is a physical change, okay? Then obviously the chemical one would be A, because you can see that there's a difference going on here. Here you have hydrogen and nitrogen, and then all of a sudden on this side, you have ammonia. They are not the same, okay? So you have that. Then you are asked to calculate what? That now consider A. So we are looking at A, which is a chemical change, or a chemical change or a chemical reaction. It says that now consider A. State the law of conservation of mass. I'm not going to write it in words. I'm not going to write it. It's going to take a long time. So I'll just say it because you're familiar with it. The law says that matter cannot be created or destroyed, but may be changed or may be transformed from one form to the other. When you say that, you get your 2 marks. Now, with the use of calculations, determine whether the law in this is obeyed or not. Yeah, so the calculation is going to be similar to what we did. You write the formula down, and then you follow the same thing, this calculation, and then when you do it, you will see that it is like that. So this is how the reaction is going to be. We're going to have 3 hydrogen, or maybe we should do it, I don't know. It might take a long time. So let's say 7.2.2. So I'm going to have 3 hydrogens like this, plus 3 hydrogens plus this, plus your nitrogen will give you ammonia, NH3, 2 of them, okay? So you can say mass of reactants. These are the reactants. So you have to write something like 3 here into brackets, okay? Hydrogen, the atomic mass of hydrogen is 1 times 2. So you have that. Then you come to nitrogen, plus nitrogen is 14, but there are 2 of them. So you say 14 times 2. Then you go here. Okay, so we end here, sorry. This is for this one. And when you do this, I think you are going to get 34. Check it, 34 grams. Then you do the same thing, mass of product. The product is this one, your ammonia here. So you say 2 to brackets, you have 1 nitrogen here, so it's 14 times 1 plus the hydrogens are 3. So hydrogen is 1, but there are 3 of them, 3. And when you do that, you're also going to get 34 grams. Okay, 34 grams. So you say, therefore, mass of reactants is equal to mass of product. Then you get 1 mark for that. So this is the last time I'm going to do this long calculation because it's going to take too long. Now let's move to the next one. The next one is, it says that study the 3 equations that are represented below. You have hydrogen combining with oxygen to give you water. Then you have liquid water changing to solid. And then you have this reaction, the potassium chloride breaking down to give you potassium chloride and oxygen. It says, which one of the equations represents a physical change? This is a chemical change because you have hydrogen and oxygen are different from water. So this is chemical. This one is water, but it's in a liquid state, water in a solid state. So this is a change of phase or a change in the state. So this is physical. So this is chemical, this is also chemical, and this is physical. So the physical change is this one here. So we put it as what? I. Okay. And then the second question says that which is a synthesis? So synthesis is one of this, either the first or the third one. Remember, synthesis is when you have 2 or more substances coming together to give you one. So this is a synthesis reaction. Hydrogen plus oxygen to give you water is synthesis, okay? This is an example of decomposition. So the synthesis one is the first one. So you have that. Now, how does the energy change in one compare to that in equation 2? So we are comparing equation 1 and equation 2. When I showed you that table of comparison between physical and chemical changes, I don't know whether I should go there quickly so that those of you who don't, perhaps you may not remember, yes, this table. I say that in terms of physical change, the energy change is low or lower, and this one is higher. Okay, so that is what is being requested here. Let's come back quickly with respect to this one. Yes. So how does the energy change in 2 compare with that one in this one? So you say that one in 1, which is a chemical reaction, is higher than. So you use this one, higher than, because that is a chemical change. The energy change is higher than that. Then the next one says, was energy supplied or removed from the type of change that occurred in two? Give a reason. So if you are changing from liquid to solid, is cooling. So energy is removed. It's like putting liquid water in a fridge. So energy is removed from the system. So we say energy is removed. So here, energy supplied or removed. We use the word removed. And then the reason is that when you change a liquid to a solid, it's cooling, and cooling requires removing energy, something like that. Then state the law of conservation of mass. You say matter cannot be created or destroyed, but may be changed from one form to the other. Now show that the law of conservation of mass has not been applied correctly in equation 3. Now, because equation 3 is not balanced, yeah, I suspect it's not balanced, because if you look at this, this is 2 and this is 3. So oxygen is 6 here, but oxygen here is 2, so it's not balanced. So basically what you do is you do the same equation. I don't want us to waste time on that. You do the same equation as, the same calculation as the mass of reactants you calculate, mass of products you calculate, and you will see that they are not equal. So you show that they are not equal. And then they say apply the conservation correctly. It means that you balance the equation. In the case of this, you balance the equation. Excuse me. If you're balancing the equation, this one should be, this one here should be changed to 3. Okay, so let me put it like that. To balance the equation, it should be 2 KClO3 to give you 2 KCl plus 3 oxygen. So something like this, and then you are done with that. Then let's move to this one quickly. Classify the following as physical or chemical change. Iron metal is melted. Explain. Melting of iron is just a change of phase, or it's change of state from solid to liquid. So we say it is a physical change. So this is a physical change, physical. And the reason is that the iron is changed from solid to to liquid state, and there's no change in the chemical composition, so we leave it like that. Then 6.1.2, gray hair is dyed to red color. Your gray hair, I think maybe some of your parents or grandparents sometimes use dye to dye their hair, okay? So it's a physical change because when you wash it, it disappears. So we say it is a physical change. So this is physical. And the last one is rusting. Rusting is the when you put iron, any iron in an open place, and then it rains and the rain, water falls on it. Over time, it changes color. It becomes like you have applied soil to it, even though there's no soil. You can peel it off and it looks brownish. Okay, so that is a chemical process. So this is chemical. Yeah, something like that. Then we come here and it says that what type of a reaction is indicated by the above reaction? This is a decomposition reaction. You start from one product, breaking down to give you 3 products. So this is decomposition. Okay, it's not synthesis, it's decomposition. Now, with respect to this, that by the use of calculations, prove that the law of conservation of mass is true for this reaction. Now, this is going to take us a long time to do it. I don't think we have time. But you follow the same principle as I did with something like this. Yeah, you calculate these mass of reactants, you calculate the mass of products, then you check if they're equal, it means the law has been obeyed. If they are not equal, the law has not been obeyed. So you use that. But the only caution I have to give you is that this substance here, PB, is called lead. It's in the same group as group, I think it's group 4. So you will have to go to the periodic table, and then it's in the same group as group 4, group 14. You have to go down from carbon And then you go down. The last one is lead, which has a relative atomic mass of 207. 207. Okay. So you do that. Or maybe I should do it. I don't know, because of the complication of this one. I'm worried you may have a problem with this. But so let me try to do it so that you don't, because this is a bit complicated. So let's look at how it's going to be done. I'm interested in this one. Okay. So we say mass of reactants. We're going to use this one. We put 2 here. This 2 is outside, so we put 2 here. And then we'll put a square bracket here because there are so many brackets. The lead PB is 207 and it's only one of it. So we say 207. I say times 1, but it's not necessary. Plus, now when you have something like this, let me put it like this. This is NO3. This is the nitrate 2. This 2 affects the oxygen and it also affects the nitrogen. So the oxygen is now 2 times 3 is 6. Then the nitrogen is 2 times 1 because this is 2 times 1. 1 is supposed to be here, but we don't write it, okay? So to put it in proper context, we're going to have something like this. Then plus the nitrogen, atomic mass of nitrogen is 14, but they are 2. So it's a 14 times 2, okay? Then plus oxygen, atomic mass of oxygen is 16, and they are 2 times 3. So that is 6 times 6, okay? So you multiply this 16 by this, multiply that by this, then you add all of them. Then when you finish, you multiply by 2. Let me repeat what I'm saying. You say 16 times 6, you write the answer. 14 times 2, you write the answer. Then you add all of them plus this one. Then the answer you get, you multiply it by 2, and you will get 662 grams. Okay? Then you do the same thing for the product. For the product, there are 3 products here. Let me try to erase this one so that you see what I'm talking about. There are 3 products here. You have this one, you do a calculation for this one, you do a calculation for that one, do a calculation for that one. So the mass of products, we'll start with 2 here for the lead. There's 2 in front here. Okay, there's 2. Then the lead we said is 207. Then the oxygen is 16. Okay. So we put it like that. Then we move to the next one. This 4 affects the nitrogen and then oxygen. So you put 4 outside here. And then you can put this one like this. Nitrogen is 14 times 1. So it's 14. Plus oxygen is 16 times 2. That's 16 times 2. So that one is oxygen like that. Then the last one is oxygen. This is 16 times 2. 16 times 2. So we calculate this one is 32. This is also 32. So 32 plus 14 times 4. Then you add this then times 2. And then when you do that, you basically going to get the same thing, 662 grams. So it means the law has been observed. Okay? Then obeyed or observed is true. This one says when this grams of lead nitrate is heated, you get this grams of solid produced. What mass of gas will be produced? So this is what you are starting with. So this is the amount here. And this one is the mass of the solid. This is also a solid here. So the mass of the gas, these are 2 gases, nitrogen dioxide and oxygen. Okay, so you just subtract. You say this one minus this will give you what is left of this. Remember I said whatever you start with, you must end with it. If you recall, I gave this illustration of going on a tour. If you are 20 students and you get there and there are 18 students, you will have to look for the 2 other students because they can't just vanish like that. Okay. So here, you're just going to see the mass of the gas is going to be 662 minus 4,46. And then you get your answer. Then it's 2 comma something. Yeah, I think I did it. It's 2. I don't get 2,16 grams. It's for the two gases, not one. All the two, because the mass of this one plus the mass of this one plus the mass of this one must be equal to the mass of this one. So if you know the mass of this one and the mass of this one, you can have the mass of the two gases combined. And that is what I have here. Okay. Okay, so this is the last question we are going to do. It says magnesium ribbon burns in oxygen with a bright white flame. Flame is like a light. And I told you that one of the evidence of a chemical reaction is the production of light. When you see a bright white flame, it tells you that the reaction is a chemical change. Anyway, so let me start again. Magnesium ribbon burns in oxygen with a bright white flame to produce a white solid, magnesium oxide. Name the type of chemical bonding in this. So magnesium is a metal, and therefore this is metallic bonding. Metallic bonding, which we have done earlier on. And then magnesium oxide is ionic bonding. Remember, magnesium is a metal, oxygen is a non-metal, so the magnesium releases 2 electrons, the oxygen takes the 2 electrons, they form cations and anions, they're attracted to each other. We did that, so this is ionic bonding, okay? Now, is the reaction between magnesium and this one physical or a chemical change? Is the reaction a physical or a chemical change? So that is the question we have to investigate. Like I told you before, it is a chemical change because even by looking at it, it said a white flame is produced. So that should tell you. And secondly, you are forming a new product. You started with magnesium and oxygen. You are producing magnesium oxide. So they cannot be. There has to be, I mean, a change has occurred. Okay. So this is what is called a chemical change. So this is chemical change. Then this one says that write down the balance equation for the reaction. Write down the balanced equation for the reaction that is taking place. Write down the balanced equation between magnesium and oxygen. So what do? You say that magnesium is Mg plus oxygen is O to give you magnesium oxide. So this is MgO. Sorry, this is oxygen. So to balance it with, like I said, there are two ways of doing it. You can do it the quick way, which is by just putting 2 here. Put 2 here, the 2 affects the whole thing. And then you put 2 here, and then it's balanced. If you don't want it to, you can do how I did it previously, magnesium plus oxygen to give you magnesium oxide, okay? So because of this oxygen here, we can put half here. And then we multiply 2 by 2. This one becomes 2, this times 2, they cancel out, it remains oxygen. And then this one becomes, so this is that. Now, for the last one, like I said, I think it will be a waste of time to do this calculation again. All you have to do is, so this is the balance equation. This is 2mg plus oxygen like this, give you 2mgO. So you say mass of reactants, then you take this one plus this one, then you do the calculation, write the answer. Mass of products, do the calculation, but you do it with respect to this one, and you see that they are equal. So this is equal to that. Therefore, the equation is obeyed. Okay. So thank you. This brings us to the end of today's lesson.